Hello students, I am Aparna Kedari and I am working as a assistant professor in Department of Chemistry, Sarhat College of Art, Commerce and Science. Today we are going to study stereochemistry and our topic is optical isomerism. So let's start with optical isomerism. First, to study this optical isomerism, we must know some definitions about optical isomerism. First is the ordinary light. Light is a transverse wave motion, and ordinary light consists of ray of different wavelength vibrating in planes, all possible planes, and perpendicular to propagation direction of propagation. This is the ordinary light. That is, light is a transverse wave motion, and ordinary light consists of different rays of different wavelength, and they are vibrating in all possible planes perpendicular to the direction of propagation. Next is the monochromatic light. Mono means single, chroma means color. Then a light of one color which consists of single wavelength with the vibration taking place in all planes perpendicular to the path of propagation is called the monochromatic light. That is, it is light of one color or single wavelength with the vibration taking place in all planes in and perpendicular. It is perpendicular to path of propagation. It's called monochromatic light. Then next is the plane polarized light. When an ordinary light or monochromatic light is passed through Nicol prism, its transmitted light vibrates only in one plane, and that is ordinary light vibrates in all possible direction, but this plane polarized light vibrating only one plane, and a ray of light whose waves are vibrating in one plane at right angle to the direction of propagation is called the plane polarized light. Then optical activity. Then when plane polarized light is passed through the solution of certain organic compounds, then like lactic acid, cane sugar, glucose, 2-chlorobutane, it is observed that plane polarized light gets rotated about some angle which emerges out of the solution of organic substances. This property of compound by which it rotates or changes the plane of polarized light is called optical activity. Then polarimeter is the instrument which is used for the detection of measurement of optical activity of substances called polarimeter. Here is the ordinary light, and this ordinary light propagates in all possible direction. When it passes through Nicol prism, then it vibrates in only one plane right angle to the direction of propagation, and this light is called plane polarized light. Then next, here is the solution of organic compounds, and when I rotate the plane of polarized light to the right hand side, it is dextrorotatory, and when it rotates to the left hand side, it is levorotatory. Then next is the optical activity. First, configuration, the arrangement of atoms or groups around the chiral center that characterizes a particular stereoisomer is called its configuration. Then first, dextrorotatory, it is denoted by plus or small d. If the optical active compounds rotates the plane of polarized light, that is like this, it rotates the plane of this plane polarized light to the right or in clockwise direction is called dextrorotatory compound. Dextrous means right, and it is denoted by plus sign and or d, small d. And the levorotatory means if the optically active compounds rotates the plane of plane polarized light to the left and in anti-clockwise direction is called levorotatory compound. Levo means left, and it is denoted by L or minus sign. Here two isomers, one is L plus lactic acid and D minus lactic acid. That is, this first isomer rotate the plane of plane polarized light to the right hand side, and the second isomer rotate the plane of plane polarized light to the left hand side. Then next is the specific rotation, and this specific rotation is denoted by alpha lambda t. Then optical rotation depends on the concentration of solution, and the length of polarimeter tube And the length of polarimeter tube, temperature and wavelength of monochromatic light, and the solvent optical rotation of compound commonly expressed as a specific rotation. Then definition for specific rotation is it is the number of degrees of rotation caused by a solution of 1 gram of compound per ml of solution in a tube of 10 centimeter long at specific temperature and wavelength of light, and it is given by the equation that is specific rotation in degrees is equal to alpha observed C into L, that is our observed rotation in degrees and path length in the decimeter, and here concentration in gram per ml. Please consider here lambda and T. This is the mathematical equation for the specific rotation. It is the number of degrees of rotation caused by solution of 1 gram of this compound per ml of the solution in a tube of 10 centimeter long and at specific temperature, and the wavelength of light. It is given by this equation. Then next is causes of optical activity. Optical activity is property related to three-dimensional structure of the molecule, and when molecule and its mirror image, this is molecule and its mirror image, are non-superimposable to each other, shows optical activity. If molecule is dextrorotatory, then it is in its mirror image will be levorotatory. Suppose this compound or molecule is dextrorotatory, that is it rotate the plane of plane polarized light to the right hand side, then this its mirror image isomer rotate the plane of plane polarized light to the left hand side, then or it is Leo rotatory. Then chirality, the non-superimposable mirror image relationship is described as chirality. That is, any object or molecule is chiral if it is non-superimposable with its mirror image. Therefore, all chiral molecules are optically active and all achiral molecules are optically inactive. Then next, asymmetric carbon atom. The asymmetric carbon atom is necessary for the optical activity. Therefore, definition for this optically activity, asymmetric carbon. A carbon atom to which four different atoms or groups are attached, it is called asymmetric carbon atom or chiral center. It is given by asterisk mark. Here at asterisk mark is given. Then a carbon to which four different, suppose this we consider this compound, then this OH is different hydrogen and fluorine and bromine. A carbon atom to which four different groups or atoms are attached, it is called asymmetric carbon atom or and chiral center. Then compounds containing asymmetric carbon atom are capable of existing in isomeric form, and the number of such isomers is given by the formula that is A is equal to 2 raised to n. A is number of isomers and n is number of asymmetric carbon atoms. Then first definition of enantiomers. Optical isomers which are non-superimposable mirror images and it rotate the plane of plane polarized light equally but in opposite direction are called enantiomers. Here there are this molecule and its mirror image, and they are non-superimposable mirror image and they rotate the plane of plane polarized light equally but in opposite direction. Suppose this isomer rotate by 30 degree to the right hand side, then this molecule rotate by 30 degree but in up anti-clockwise manner. Therefore, enantiomers are the optical isomers which are non-superimposable mirror images turning the plane of plane polarized light equally but in opposite direction are called enantiomers. Then next is the absolute configuration. The description which gives the arrangement of four atoms or groups in a space attached to the chiral center is known as absolute configuration. Then there is R configuration and S configuration. The R stands for Latin term rectus, meaning right-handed, and the S stands for the Latin term sinister, meaning left-handed. Then sequence rule for this determination of configuration. The first rule is for rule 1, that is atomic number. The atoms or groups are arranged in order of decreasing atomic number of the atoms directly attached to the chiral center. Then the atom with highest atomic number is assigned as a first priority, and the atom with lowest atomic number assigned fourth priority, that is last priority. Then the order of priority of atoms. Suppose here these are atoms and the atomic numbers of this atom, that is iodine is 53, bromine 35, then chlorine is 17, sulfur is 17, 16, and phosphorus is 15, fluorine is 9, oxygen 8, nitrogen 7, carbon 6, and hydrogen. Then they are arranged first priority to iodine, then bromine, chlorine, sulfur, phosphorus, fluorine, oxygen, nitrogen, carbon, and hydrogen. Then rule 1b is if the directly attached atom is same to the chiral center, then or two atoms are directly bonded to the chiral centers are isotopes of each other. Isotopes of same element. The atoms of higher mass number has highest priority. For example, hydrogen, there are three isotopes of hydrogen: tritium, deuterium, and hydrogen. And its mass number, that is, it has these isotopes has same atomic number, but they have different mass number. Here, mass number of tritium is 3, mass number of deuterium is 2, and the mass number of hydrogen is 1. Therefore, if these isotopes are directly attached to the chiral center, then first priority will or highest priority given to the isotope which has highest mass number. Then rule 2, next atom. If two identical atoms are attached to the chiral center, then priority is determined by comparing the atomic number of next set of atoms. Here, if this is chiral center, then here all are carbon atoms. Then first priority is given to this carbon which is attached to three other. This carbon atom here, carbon atom, carbon, carbon. This directly attached are carbon atom. Then see next atoms. Here this carbon is attached to next three carbon. Here it is attached to only one. Here it is attached to two. And this carbon, there is no other carbon. Therefore, first priority to this group. Then second priority to this which is attached to this carbon which is attached to two other carbon atom. Here this carbon which is attached to one other carbon and CH3. In second, here directly attached atoms are carbon to the chiral center. Then priority is given to the chlorine, OH, and nitrogen. Here chlorine is atomic number of chlorine is 17, oxygen is 8, and nitrogen is 7, and carbon 6. Therefore, here first priority goes to this carbon because the next carbon is chlorine. Its atomic number is higher than oxygen and nitrogen. Then second priority to CH2OH because here next atom is oxygen, and third priority to this CH2NH2 because nitrogen 7 atomic number, and here CH3. This is the sequence rule 2. Then sequence rule 3 is groups containing double or triple bond. If the groups directly bonded to the chiral center contains double or triple bond, it is considered to be equivalent or two or three single bonds with the same atom respectively, and then the sequence order is decided. Here this carbonyl, then here carbon oxygen double bond, it equals to it is considered as this carbon is oxygen attached to two oxygen atom. Here carbon carbon triple bond, this carbon is attached to three other carbon atom. Here this if phenyl ring is present, then it equals to three other, that is here two double bonds and one single bond, that is it is attached to total three carbon atoms. Then when there is carbon-carbon double bond, then it is equals to this carbon is attached to two other carbon atoms. If there is carbon-nitrogen triple bond, it equals to carbon is attached to three other nitrogen atoms. Then here nitrogen, it equals to these two oxygens, and here nitrogen oxygen double bond, therefore it is attached to two other carbon. It is considered as this nitrogen is attached to two other and this third oxygen, therefore total 3 oxygen atom. This is sequence rule 3. Then for example, the determination of R and S configuration. This example, in this is chiral center, and to this chiral center one atom is iodine, second is bromine, chlorine, and hydrogen. Then this do first exchange, and in first exchange always here priority. First we have to check this priority. Then first priority is to the iodine because it has highest atomic number. Then second priority to bromine, then chlorine, and then hydrogen. Therefore this is first priority group, second priority group, third atom, and third to chlorine. And then in first section always do the lowest priority group we should bring to the bottom, bring to the bottom. Therefore in first exchange the hydrogen is bottom and bromine is at the place of hydrogen. Then in second exchange you can do any exchange, that is bromine iodine, iodine chlorine, or chlorine bromine. Then decide one first, first priority, second, third. Forget this about this four priority group. Then it rotates 1 2 3, it rotates clockwise. Therefore this configuration is R configuration. Then next example, hydrogen, phenyl, and bromine, carbon carbon double bond. Then priority wise this bromine is first, second to phenyl, third to this carbon carbon double bond, because here in phenyl this carbon is attached to three other, and here this carbon is only two carbon, and here is hydrogen. Therefore first, second priority, third, fourth. In first section always bring this lowest priority group to the bottom, and therefore there is this double CH2 at the place of hydrogen. And in second action you can do any action, and here according to priority wise 1 2 3 it rotates anti-clockwise. Therefore this configuration is S configuration. Here compounds containing two chiral centers. Okay, this is all about the compounds containing one chiral center, configuration of these isomers, enantiomers,